Hello everyone, my name is Guillaume Mestdagh and I am a postdoc researcher in the INRIA TRIPOP team in Grenoble in France. Today I will tell you about some work in progress about dynamic simulation of aerial ropeway cable. So this is a work started in the PhD work of Charlie Bertrand, and I recently put my hand into this. So by aerial ropeway, I mean cable transport, so chairlift, cable cars, and all other vehicles fixed to a running cable to transport people or things. So maybe some of you have already been on this kind of transport. You can find them in ski resorts, but also in cities to reach touristic sites, but also more and more for daily commuting instead as an alternative to tramways, bus, and so on. So it's a cable supported by pylons with at each end of the installation a station so that people can get on or off vehicles. So a risk with this kind of transport is due to dynamic effects. I mean, when the vehicle or the cable are shaken, they can fall, or the cable can fall from the pylons. So source of dynamic effects include the wind, so don't go on a chairlift in the middle of a storm, but also emergency stop. On this picture, we see the Mont Blanc cable car that had to stay stopped for one night because the cable had mixed up after an emergency stop. And also, in recent installation, vehicles are going faster and faster, so maybe this can cause some dynamic effects that are not really studied right now. We are working with the STRMTG, which is the French public service that checks the security of cable transport installation, existing one, but also a new one that will be built. And they need a simulation software to investigate past incidents or to check the security of existing and new installation. And no open source software exists right now, hence the project. So in this presentation, I will first give a few details about the cable model we use and the numerical methods. I will show basically how the software works and a short numerical example. So the cable is modeled as a 1D media, so a line whose position is denoted by Q, which depends on time and the curvilinear abscissa S. So the deformation energy of the cable is this formula. So this is the strain, and we only penalize positive strain. So the cable only resists to extension, no resistance to compression, and no resistance to bending, torsion, or anything else. So cable in compression, no stress, and cable in extension, linear stress. Concerning external forces, for now we only consider the weight, so the own weight of the cable, and some discrete masses due to the vehicle attached to the cable on a discrete position along the cable. Concerning the modeling of the installation, the cable is in contact with some supports that some towers that either keep the cable away from the ground, but they can also compress it to keep it not too far from the ground. And there are some stations at the extremity. So every supports are represented as cylinders for simplicity. For instance, the towers contain a lot of little shifts, but one tower with its curvature will be represented as one cylinder for simplicity. On each cylinder, we have a quite low friction coefficient, which represents the resistance of sheave to rotation, except on the driving sheave, so at this station, which is the one which puts the cable in motion by friction. So this one has a high friction coefficient because we are not modeling the resistance, but the real friction between the sheave and the cable. And the non-penetration condition between the cable and the obstacle is denoted with the letter G. And we will speak of friction later. Let us have a look at the cable model. So the position is denoted by Q, and this is the Lagrangian function for the cable, so including kinetic energy, the global deformation energy, the energy due to external forces, and one term due to the normal reaction. So we have no friction for now in this Lagrangian function. And I would add that the contact constraint is a no. How does it work? Okay. The contact constraints are imposed at node, so we have basically one normal reaction vector, but coefficient, I would say, per node. So from this Lagrangian, we can derive a Euler-Lagrange equation, which looks like that. V is the velocity of the cable. It is Q equal to Q dot. We have the internal forces, external forces, and the reaction force. So we have added the conservative forces that don't fit in Lagrangian, the tangential friction forces. The contact is 2D, which reaction forces are only one tangential and normal component. Concerning the integral scheme, we use a very simple implicit scheme. Here I put the implicit Euler for the city, but actually I have a data scheme in the software. And the step of velocity between step k to step k plus 1 is the sum of the contribution of the regular forces, so internal, external, and the contribution of contact forces. That can be impulsion, but actually what we want to do is not to characterize them, it's just to compute their contribution along the time step, the accumulated contribution. So by doing some calculation, we can express the velocity at the next step as the sum of the velocity we would have without contact plus that comes from the impulsion of contact forces. We have the same, here we have the same expression, but we are passing the local frame. So the component of these vectors are with the each node with the normal and tangent vector. And so if we, I'm not sure I'm really understanding how the passing works. Okay. Yeah, so if we zoom on one node, so we have the velocity vector is made of normal and tangential components, and same thing for the reaction vectors. The local system at this node looks like this. So the first line is, we have seen this system many times in the Congress, right? So the first line comes from the equation of the first slide, of the previous slide. This is the complementarity condition for due to the non-penetration condition, and this is the Coulomb friction condition. So I won't get into details, but this system in 2D is quite easy to solve explicitly. And to solve the whole contact problem at each step, we use simply a Gauss-Seidel iteration, meaning that we fix every node but the one we're interested in. We solve the problem with all other coordinates fixed. Then we pass to the next node. And we keep iterating with on every active node until convergence. Okay, so now for the functioning, just the pipeline of the simulation we have. So the first step, when we have we input the coordinates of the towers actually. So we first have a first guess of the shape of the cable using explicit the catenary equation, which is the explicit formula for a cable hanging between 2 points. And it gives so first a first approximation of the shape of the cable. And then we just relax this approximation to match also to respect the contact with the, so this should be circle, but the image is compressed here with the support, just by running some simulation step with a big damping so that the solution, the cable relax to a static equilibrium position. And once we have this, we can put the driving sheave in motion. And so I will show you a small video of an example we have. So this is on an installation that used to be existing, but it has been dismantled now. Okay, so this first motion is actually the damp simulation, but now the little triangles are, I don't know if you see very well, the little triangles are the vehicles. And so basically it's not very impressive, but we have the simulation of the installation running. Okay, maybe it's a little too long, but in 30 seconds there will be a stop to show if there is some shaking in the line. Maybe we can. Okay, so it's 30 seconds. So now, okay, there is a stop, and we see that actually there are two. The two spans, the two larger spans, have a kind of oscillation movement. So it's not very impressive on the video, but for people on the vehicle, it's several meters of motion, so they somehow feel it. And for the simulation, so it's difficult to say this after the previous presentation, but we take approximately 1 hour of calculation for 1 minute of simulation. And so we can gather some information such as so here it is in orange, it is the envelope of velocity of all nodes to see if some of them go too fast, and same thing for the tension along the cable here, and the black trace is for one node. It's just an example. So this kind of statistic we can get to for the industrial partner to check that the installation satisfies some norms or requirements. And we have tried to, so this is also still work in progress, but we have tried to reduce the time step to see if the solution converges towards something, and it seems like we are the time scheme look consistent. I won't comment on the slope because it's still work in progress, but it's encouraging. And okay, to conclude, we start to have a working proof of concept for dynamic rope race simulation that will help regulator study the dynamic property of real installations. And so, as you can see, there is a lot of things to improve in this software. So first, the industrial partner is asking for new features like potentially put different masses for vehicles so that to make a difference if there are people or not inside. And in terms of numerical method, we want to use higher order elements and maybe better contact solver to pass at scale for larger numbers of elements. And that's all. Thank you. Okay. So if you have no question, yeah.
I was wondering, is this problem a unilateral problem physically? So if the cable is under tension, is there any possibility of separation?
Is there a possibility of separation?
So my question is this problem physically a unilateral problem? Can the cable separate? That's not.
So
if I consider that the cable is under tension, then it might not separate. So that's why I was wondering.
So at least on the towers, there are some example, some existing accidents where the cable has jumped from the towers, and on the towers actually there are some metallic arm to catch the cable if it falls from the. So it's possible, but usually it's if there is a risk, they had a second rank on.
So it's possible. So it's important to consider.
Yeah.
Another question. Can you comment on how you enforce the elasticity laws? Because you wrote on slide 12, I think that you have the gradient of the potential, but it's implicitly included. You saw the Newton method there before contact, or is it included in the contact group side?
Yeah. So it's a tricky. So yeah, actually, it's not really. It's not really implicit. So actually this the gradient function is linearized. So this as you say in the free step, this is approximated by a linear approximation from QK. So QK plus the Hessian of psi times QK plus 1.
Reducing your free velocity, not the impulses.
Yeah, we compute the free velocity and then only the contact. It's also something we will look into in the future. Okay, so if there is no other question, I will present you. Sorry, Jonas.
I will talk after the few.
Okay, let me. So Jonas is about to tell us about one element for rockfall protection from a net that protects the road from a rockfall from cliffs.
Yeah,
So Jonas is coming from the University of Stuttgart and is an expert in high order non-smooth numerical schemes.
Okay, thanks a lot. Yeah, I promised to present some efficient finite element methods for rockfall protection with ring nets. And this is a work based on an excellent bachelor student, which is quite impressive for me. So keep that in mind. Some slides are very simple, but it's a continuing work of a bachelor thesis. I'm very proud of that. And the animation here is a real simulation using polyhedral grains. So it's quite impressive that the student could manage to do such a thing. So I hope to convince you with that in the beginning. But let's get started. What's the idea? So I want to have a model that is both robust, efficient, and can capture heterogeneous multi-body systems, like such a protection net, which consists of elastic parts, some very rigid parts, these large boulders, maybe also the ground. And in a dream world, I would like to build this on a rigid body code structure because it's very versatile. We can use all the nice collision detection stuff from that. But we have to handle high stiffnesses and want to remain modular. And it turns out that it's quite opposing direction. So let's see if this worked out. So that's the main motivation behind that. And to get started, I prepared a few points on rigid body kinematics and dynamics, which I think is quite useful here because it's more in the finite element region. So maybe you can learn something about rigid bodies here. The basic point is we have a configuration made of the center of mass of a rigid body, and we have to somehow describe finite rotations. And it's a classical thing to use quaternions there, which let's say there are 4 real numbers with some calculus rule behind it, and we can use them to have 7 coordinates for each rigid body in positions. And with that, we can approximate or compute, not approximate, compute elements of a rotation group and their time derivative. And it turns out that it's related to the angular velocity of the body. So a very clever trick is there to use, in contrast to the time derivative of the generalized coordinates, new generalized velocities. So the velocity of the center of mass and the angular velocity. And this allows us to relate time derivative with the generalized velocities. And we get a very nice simple dynamics from that. So it's worth to have this non-trivial kinematics here. And then a simple thing, but we can address arbitrary points in the rigid body by going from the center to some point using this vector chain. But it's important for defining context, for example. And the same applies for velocities. We can compute the velocities of a point by more or less applying a very simple Jacobian on the generalized velocities. This use again. And this Jacobian is everywhere. For every contact, we have to compute this Jacobian. So it's very nice to have a cheap and simple structure here. And this is the kinematic part. And if we go on to kinetics, we can simply use the Newton-Euler equations, or we can derive them. It doesn't matter. In the end, we have this set of equations, which is very simple. So we have a diagonal part for the translational velocities or accelerations, and typically also a diagonal part for the inertia, if we choose the right basis for this tensor here. We have external forces and moments, and one point which is not that nice is that we have a bilinear geosymmetric gyroscopic term here, which is troublesome in highly dynamical systems. So we have to cope with that, but otherwise it's very simple, and we can compute such Johnny Beckhoff style flipping rigid body very simply. But we want to go on. So if we want to describe a double pendulum, we have to add some constraints there. And in fact, it turns out that we can do this by going over complying force laws, and in the limit they get some constraints, so we can connect rigid bodies to get some hinges realized. So for simplicity, imagine we have a force law, and ignore this minus sign here, it's just by convention, that is given by a constant diagonal matrix, which I extract from the force law, times some nonlinear function which defines a spring elongation, something, whatever you like. The issue is, if I add this to the dynamics, so it just directly enters the dynamics, we have problems when we have high stiffnesses. So it's really tough to solve these methods in a stable way, so the time integration gets really problematic. And an idea, if you work a lot with differential algebraic equation, it's quite obvious that we can, instead of adding this to the dynamics, we can add an algebraic relation where we change the stiffness to a compliance and put it on the other side, and then there's no issue if we let the stiffness go to infinity, because we can simply remove this term here and end up with a bilateral constraint. So it's just an algebraic equation in the end, but it has to be solved implicitly, so it's nonlinear. Implicit solving this requires some type of Newton method, which possibly gets again slow. And again, an idea borrowed from the DAE theory is Why not do index reduction on that? So differentiate this equation on velocity level, let's say, stiffness or compliance is constant, so we get an evolutional equation for this force, but be aware of that we cannot invert this since it might be zero. So we just add a possible singular equation in the derivatives here. But we have to cope with constraint drift. Okay, that's the price of reducing the index. And yeah, that's just a formal thing. We can add now these forces here, or the force measures, to deal with impacts later to the system. So we have our kinematics, dynamics, and this additional algebraic equation on velocity level. And to give you a very simple example, we can have a linear distance spring. So you have 2 points, connect them, constrain their length to be some reference length, and then you can simply compute all the tools you require to formulate this force law. Yeah, and this is quite simple, but using these methods, we can build more or less arbitrary constraints, and this allows to do some nice mechanism here, which is built by over 800 constraints and 300 rigid bodies, and it's quite popular, these strand beast walkers, purely driven by gravity or by some wind. Okay, but I promised to present Khosara model, and up to now it was only an introduction because I built a Khosara model exactly based on these ideas. So it started all by a former student of mine, which works a lot on rod theory with me, and now he made a very nice publication on a mixed finite element model, and I had a look at the equations, and I thought, okay, why not do a very specific integration on the virtual world? So the spatial integration is done in a very specific manner, then we end up with a rigid body code. That's what the idea. And it turned out that's really doable. So if you assume linear interpolation of the center line kinematics and the quaternion field, we end up with some discrete virtual work contributions, and they can be integrated differently. So I used the trapezoidal rule for inertia and external parts, and it turns out I get really simple rigid body mass matrices, gyroscopic forces, and external forces. And for the internal interactions, I use a one-point quadrature, Gauss-Legendre, and what you can see, if you really derive the equations, you see you end up with a compliant force law, a single force law between two bodies interacting on both involved bodies. So it's, in the end, it's, I write it here, it's a collection of n+1 rigid bodies with n compliant force laws in between. So it really reduces to rigid body with complex interaction. And I also prepared some details, which I hope to get published with a colleague soon. You need some quaternion stuff here, so the mapping from the quaternion to the orthogonal group, the differential in matrix form. Ignore the terms if you do not know them a bit. They are just appearing in the strain measures. So the strain measures really known for Khosara rods are axial, shear, bending, and torsion strains. And they are simply given by differences of the positions. If you have a single node or a single two-node element, and the differences of the quaternions mapped with some, let's say, strange matrix to be a strain measure. And the last missing piece, or not the last, for linear force law, you can now obtain the very easy diagonal C matrix for the compliance. And if the force law is linear, you get just the difference of the strain measures with respect to the reference strain measures. So it's really a simple linear force law for a Khosara rod. And the last missing piece is this W, this generalized force direction matrix. And again, it's quite simple. It's the midpoint orientation, then both strain measures, and then some identity depending on which side of the node you are. And yeah, it's not so interesting for the matrix, mass matrix, gyroscopic, and external forces. It really ends up with the rigid body parts you already have seen. It's just to be careful that on both boundaries of the rod, you have to add an 1/2 because of the trapezoidal rule. Otherwise, it's really the full length rigid body. And then I took my favorite example, which took me quite a while in the early days. It's really tough to simulate this Wilberforce pendulum because it's made of spring steel, 1 millimeter, and it's really highly dynamic. And if you can reproduce this, how do you say, periodic change between axial oscillation and torsional oscillation, it's really a good method to check your model and your integration method. So it's really tough to do this. So I was satisfied with this model. And now, since we are on a contact conference, obviously I have to add contacts, and I show you how this is done briefly. So most of that is quite obvious to you. So we have two bodies, 2 points on a body with a tangent plane, can define a distance, I call it Gn. And we can define contact velocities, 1 in normal direction and 2 in the tangent directions. And here the Jacobians appears. That's why I was so into them. We can add, again, impulses to our equations of motion, and we can define post and pre and post impact velocities for our time integration later. And with these, let's say, kinematics, at least on the left-hand side, we can now enforce some laws, like Signorini's law and Coulomb friction. And for Signorini's law, we do this on velocity level, so we only state this for closed or penetrated contacts, and then this inequality complementarity is imposed on velocity level. And this can be written by a normal cone inclusion or equivalently by a projection equation, and this is where we will use a lot. Same for Coulomb friction, can again be written as a normal cone inclusion with some set here, it's a disk, and again, it's a projection. So overall, we can do a global projection or global for each contact pair. We can define projection from the post-impact velocities or the generalized post-impact velocities to our forces or impulses. And now this is a really huge slide because I do not want to go into details of the integration method here because it's quite difficult, but its basic structure, I think, is clear. So we have 2 position updates. The first one with the half step and the last one. And obviously the magic happens here inside the second point. So the idea is to separate positions and velocities. So after the first half step, we freeze all the positions, do all the collision detection, evaluate all the involved matrices here for directions of forces, of what else do we have? Not much more. Let's say the force directions. And then we end up, when we apply a theta method to our velocities and these force laws, we end up with a single linear system that has to be solved. And the issue is that this system here, linear system, I call the right-hand side B, depends on the unknown contact forces and friction forces. And in order to deal with that, we somehow have to initialize these values and initialize also the unknowns velocities and these force laws. And then we can do an iteration. So we map these both initial points to a new force, add the force again on the right-hand side, solve the linear system. And this can be iterated until convergence, which can be written as a fixed point iteration. It's quite slow, but it's very, very robust. So all the examples you will see later are done with this method, and if you're not so into tight tolerances, it's really simple to do so. And finally, another explicit position update, and all is done. So as promised, some numerical examples. Yeah, the goal was to have a rockfall barrier net. I think this was a quite good test here. It's a very large boulder, and you see in the end something is gone wrong here with the collision detection. I think it's due to the non-convex shape, so there's some strange thing happening. In the end, it pulls out the rope, but that was the only boulder I found in the internet for gravity. So yeah, ignore this here. And the second thing we already have seen on Wednesday, I think, a chain winding up. It doesn't look that difficult, but to be fair, this whole rockfall protection net is much simpler than this winding chain because it's only driven by contact. So it's really tough to do this with rigid bodies. So it's a bit disappointing because it looks not that impressive, but it was really challenging. Yeah, we also find some very nice fabrics in the web, so you can download some splines of this woven clothes or something, and we applied a single rod finite element through all these spline positions and just throw them onto a sphere with self-contact, and it was quite satisfactory to see this working. And my boss is quite involved in this woodpecker toy, so I tried to do this with a helicoidal spring because it looks a bit funny. And now we try to put it to the let's say, what can we do with this type of solvers? And maybe on the right-hand side, it's quite expressive. My student found a world record in domino building, and he tried to build this with a simulation, and it works quite good. If you ignore the wall here behind that somehow changes the situation, it's really impressive to compare these two simulation on the left and animation on the right, which was slow but quite robust. So the method can resolve such things. And on the left-hand side, this slinky toy is really annoying to simulate because it's very fast, highly dynamic. It's a stiff spring, a lot of self-collision. Maybe the stairs are not optimal here, but I think it's nice to see this characteristic motion of this toy. And with that, I'm at the end of my talk. Thank you for attention, and I'm happy to answer some questions if there will be time.
Thanks for your very nice talk. I am actually curiosity. When it comes to multiple contacts like those that are on the bottom right, yeah. Can you compare this kind of method, for example, to discrete element method? You try to point out the advantages and the drawbacks of the two methods. Usually that kind of problems can be traditionally solved with discrete elements.
So I'm not in discrete elements. I think they use a potential, right? To do
the potential they facilitate like this optical resonance sphere, and there's stiffness, Coulomb and that thing, right?
Yeah. In fact, you do not have to specify stiffness here because it's all rigid. It's rigid cuboids and just Coulomb friction with a friction coefficient, obviously, but no stiffness in penetration direction or something like that. But I cannot tell you if this might be similar with another method. Yeah, possibly because it's very, very redundant. The contacts are very highly ranked efficient, so it's not that easy.
Okay. Yeah, thank you. My question relates to when you talked about bilateral constraints, you introduced compliant force laws.
Yep.
I was wondering why is that needed? Because enforcing bilateral constraints is relatively balanced outcome.
Well, it's necessary. I think it's very convenient to construct multi-body systems like that. It's not necessary. You can do just relative coordinates if you like to, but your system gets coupled. So now all these mass matrices are uncoupled. You have blocks of mass matrices.
Here you're, let's say, differential algebraic system without introducing any compliance.
Yeah.
So I was wondering, anyway, we can go back to.
Yeah. Okay. Yeah.
Okay. Thank you very much once again. Moritz, Billen, schema as a fluid structure contact interaction.
PowerPoint, please. Okay. Hi, my name is Moritz. I'm a PhD researcher in Aachen. My supervisor is Norbert Hosses, and the professor of the chair is Marek Baer. And I'm going to talk to you about the skin path rolling as a fluid structure contact interaction problem. And first, I want to start with what is actually skin path rolling. And skin path rolling is the last step in manufacturing aluminum sheeting. The idea is that we have a surface texture on the roller, and we want to imprint this texture on the worksheet for subsequent manufacturing processes. If we move one step closer to the contact, we see that there's a lubricant inside this contact interface, and this is used to reduce adhesion to the roller surface and therefore increase the roller lifetime. If we go yet a step closer on the roughness level, we see that this lubricant fills up these pockets that are actually the texture that we want to imprint, and they take part in the deformation. And the goal of this project is how can we model and figure out how the imprint looks in the workpiece in the end. This is a complex problem. There's a lot of stuff that I'm not considering, which are listed here. So all of these things may or may not have a big impact on the results. But we simplified the problem, and I already show here the geometry that I'm analyzing later. We are considering contact, a changing topology. If this roller surface is moving down and we have contact, the fluid domain splits in two and we have a changing topology. This also traps the fluid if we consider this closed on one side. And there's obviously FSI involved. Now I'm going to go through the physics field by field. So we start with the fluid dynamics. These in the lubricant domain. This is governed by the Navier-Stokes equations listed here, and we have some boundary conditions. We have the roller surface which moves down, and we want to match the velocity of that. For the trapping of the fluid, we are considering a symmetry condition here, which blocks the velocity in the x direction, and we have coupling conditions on the FSI interface. Talking a little bit about discretization, we use first order finite elements for the fluid. This requires to use a residual-based stabilization. We use SUBG to circumvent the LBB condition and use the same ansatz functions for the pressure and velocity field. We use semi-discrete time stepping, and this is an interface tracking approach, which means that the fluid is always entirely encompassed in the mesh at any time. Moving on to the structural side, we have the momentum balance on the structure, and here we consider a very simple constitutive model, small displacements and linear elastic, and the contact conditions we have seen a lot of times already. One thing to point out is that on the FSI interface, we also need to consider the contact conditions. We in the solid domain, we consider symmetric on the left and right boundary and a fixed domain below. Something about numerics, so we use a Newmark time stepping scheme. The contact surface is considered rigid, and we use the penalty contact method to enforce the contact. So before I already showed you this animation. We have these, I'm going to show it again. We have these domain topology changes, and for that, and I also said that we have a interface tracking approach. So what we need to do is update the mesh to reflect these topology changes. And for that, we use the SR-VR method. The paper is listed here, developed by a colleague of mine. And what we do there is we have a background mesh that that lives in the entire region where the contact interface or this roller interface might live, then we can deactivate and activate elements, and we do that based on the position of the boundary. So everything below the boundary is activated, and everything above is inactive. And then we can just remesh this little sliver by projecting the topmost nodes and remeshing this. This enables us topology changes, and this method was developed for large mesh deformations in fluid problems. Yeah, and this also yields us the boundary conforming property that we desire. And the remeshing effort is significantly reduced compared to fully remeshing. One small caveat, so I said we have a topology change, but if we look closely in our numerical analysis, we actually offset the contact a little bit so that we have one element thickness in the contact interface. And the idea here is, we do that by introducing a little offset of the contact interface. And the idea here is that we have continuous pressure field on the FSI boundary. Exactly. And what we do get, though, these velocity conditions, which we want to have, restrict the velocity degree here and the velocity degree here, degrees of freedom, and thus the fluid cannot escape, having yielding the entrapment that we want to model. Right. Going forward to bringing these subfields together, we have the coupling loop, and here I first show you a classic staggered approach. This is the Dirichlet-Neumann coupling. So we start with a solid solver here in this case. We take the displacements, deform the mesh somehow, then compute the forces, pass them back to the solid solver, and keep iterating till we converge. But now we have this enclosed fluid trap, and what this means is that we have full Dirichlet conditions on the entire interface of this, and this violates the continuity equation, so the field is not divergence-free anymore. And to recover this, we use the Robin-Neumann coupling scheme. So we allow a little bit of during conversions, we allow a little bit of slack on the interface by enforcing this in a weak sense. And here we have this this alpha Robin parameter, which will come back to haunt us later on a later slide. Right, so I want to move on to results, and these are very preliminary. And I want to start with a trap-free case. So now I talked a lot about the traps, but now I leave the boundaries open, so the fluid can escape and come in as it wants to. And this is how my mesh looks. And if I start the animation, I will wait a bit. Okay. Yeah, so what we would see if the animation was going, we would see that the surface goes down. The mesh is remeshed as the simulation progresses, and as soon as the boundary hits the last element layer, basically this element layer stays, and this is the layer I was talking about earlier. And the fluid escapes to each side, and the volume of these pockets does not stay constant because the fluid can escape. So now I was hoping that we have a working animation. Okay. Yeah, I will just. Oh, I cannot even continue. So I can already spoil. This is the only working result that I got. So on the next slides, we will have working is a big word in this case. Yeah, on the next slide, I tried the same thing but blocking both sides of this fluid domain. And what we would see there is if it was working correctly, then we would see a constant volume of the fluid domain. Okay, I might just wait till we have the picture. Hopefully at some point. Wow.
Did you update the presentation?
I did.
Last hour?
I think so. That was not a good idea. I wanted to add slide numbers. But if you have an older version, that's also fine. I just added slide numbers. It's nothing big changed. Yeah, I mean, for animations, it's good. Yeah, it's not huge animations. Yeah. It's not reacting at all.
That's somehow there's no progress in the download.
Oh, okay. If that helps. But it's only like 2 more slides. So, and as I said, the remaining simulations are not working correctly. So I'm also happy to not show them. No, I quit. Yes. Yep. Okay. So next, as I said, we have the fully trapped case. So both are now symmetric boundary conditions. So no fluid can escape or come in. And as I said, so the volume of the fluid should stay the same, but in this plot, I plotted the relative volume. So compared to the initial state, how the volume progresses over the time iteration. And for like sort of low Robin parameters, we see that the boundary conditions are not, or the divergence is violated heavily. So we lose a lot of mass. This can be a little bit decreased, this effect, by increasing the Robin condition, Robin parameter, but yeah, the simulation diverges even quicker than with these ones. So this is something that I still have to investigate. And finally, so this is the test case that I was talking about in all the previous slides. And now the animations are not working because it's a PDF. What I did here is I locked it on one side, and what we see here is the same effect as we saw in the previous slide, the volume does not stay the same even after contact, and the pressure does not increase at all, basically, not in a measurable way. So I tried deactivating the contact condition. Maybe that's the reason why this doesn't work. And this you would see here. And yeah, the pressure increases a little bit more, but not significantly, so we don't see any deformation on the solid body. Yeah, okay, this is all I can say about this. Okay, summarizing, yeah, we still need to do some work, but the Robin parameter can be used to capture some of the effects of this fluid volume decreasing in the outlook. So this tuning effect was seen to be reduced by using interface quasi-Newton methods, which I want to try at some point. And I also wanted to mention here that I am working with my collaborators on a trapped fluid experiment. So this is the rotationally symmetric sample, and we are upsetting the sample, and we have a little bit of a pocket on the top, and it's filled with a little bit of fluid, hopefully not as sloshy as indicated here. And then we see how this gap evolves over the upsetting. Yeah, this is all I have. Thank you for your attention, and I'm open for questions.
Thank you.
Yes, please.
Thanks for your presentation. To develop general, usually when it comes to applications, people solve the Reynolds equation, the first one version of the
No.
equation, where you like the inertial terms, and then you use a point solver, but because of the problem complexity. And sometimes you need, when you have roughness, even to homogenize them using the so-called performance. Have you comment about your approach, or why you think that Mestdagh is better in this case?
I would say it's kind of the history of our chair is in fluid mechanics, and this is where we are coming from. So the solid is new for us, and we have a lot of knowledge about the Navier-Stokes equations and how to solve them. So that's what we use. We use all these methods that we have developed for this problem, and yeah, I also realized that it would probably make my life easier if I would use the Reynolds equations, and I'm still thinking about that. But at the current time, I'm looking at this.
When it comes to fluid, do you have any idea about the ratio between the inertial forces and the viscous forces? That is usually the parameter that you should have.
Yeah, I guess yeah, I think the inertial forces are quite low in comparison to the viscous forces.
More questions? If not, thanks once again. Rawane, Mansour, operational formulation and numerical resolution of persistent adhesive contact in hyperlapse.
So hello everyone. First, I would like to thank the organizer for giving me the opportunity to present my work. My name is Rawane Mansour. I'm a PhD student. Today, I will present our study, variational formulation and numerical resolution for persistent adhesive contact in hyperelastic material. This study is based on the published article, an energy-consistent energy for persistent adhesive contact for hyperelastic material, carried out in collaboration with Francesco Bonaldi, Michael Barbotto, and Serge Dumont. I will start with a general introduction, then I will present the mechanical framework for our model, followed by its mathematical formulation. Next, I will present the numerical strategy based on the primal dual active set method. And I will conclude with numerical simulation demonstrating the robustness of our model. Modeling contact between deformable body consists a major challenge in numerical mechanics due to strong nonlinear and non-smooth behavior, especially under large deformation and non-smooth and dynamic condition. A representative example is the interaction between a stand on the arterial wall. Such example like this need energy consistent time integration scheme to ensure stable numerical simulation. To formalize this phenomena, I will present the mechanical framework. We consider two reference bodies, gamma 1 and gamma 2 in R3 subjected to large deformation. Their current configuration is defined by a deformation map. The position for each body is time t is given by phi equal x plus u, where u representing the displacement field. The physical behavior of each body is hyperelastic. It's fully defined by a strain density energy W, where P representing the first Piola-Kirchhoff stress tensor and F representing the gradient deformation. To describe the interaction between two reference bodies, we introduce the normal gap, d mu, which measures the separation between two bodies, and the tangential slip, d tau, which representing the displacement in the tangent plane. Contact is modeling by unilateral law, while friction is governed by Coulomb friction law. In dynamic condition and with large deformation, these two laws are not enough for energy consistency. Therefore, we use a persistent condition that enforces that power of contact force is zero, that ensures that contact neither create nor dissipate energy, giving the persistent contact law. To model adhesive in two bodies, we adopt the Talon-Corneal model. In this approach, adhesive bonds are modeled as elastoplastic element, and we introduce an internal variable, GA, which represented the accumulated plastic evolution of adhesive bond. This variable can be physically interpreted as a measure of damage or progressive decohesion. The adhesive force is bounded by a decrease in threshold S. This function representing the gradual loss of bond strength. This function vanishes when the separation GM is reached, corresponding to the maximum separation distance before total rupture. Here PM representing the initial adhesive threshold. To complete our model, we define the contact gap adhesive norm D, where the parameter S mu activates the normal contribution only in the separation phase. The adhesion force is defined as a projection onto the positive real number of a linear law, while gamma representing the adhesive stiffness. The plastic evolution of the internal variable GA is given by the complementarity system. One, it can only increase. Two, the adhesive force remain below the decreasing SGA. Three, plastic stretch start evolving only when this limit is reached. To reformulate the adhesive force, we apply a Euler scheme for our internal variable GA, which provide an explicit expression for adhesion force lambda A as a projection into the interval 0HA. Finally, the normal contribution, this force remain three main regime at the right on the figure: no adhesion, cohesion, and decohesion. Now we want to present the mathematical framework. In the strong form, we find the displacement field U, the stress tensor P, and the adhesion force lambda A that satisfy the dynamic equilibrium equation, followed by dynamic Dirichlet and Niemann boundary condition. Here, contact and adhesion are totally incorporated into the problem when the adhesion force is contact force is given by combination of lambda mu, the contact force, and lambda A adhesion force. The problem statement are completed by the initial condition on displacement and velocity. This formulation are not directly related to numerical solution. For this, we move to variational formulation. The variational formulation consists by multiplying the strong form by test function and integrating by part, which allow working on suitable functional space. Here, contact friction and adhesion appear in integral via PC plus F plus A, where delta D mu, delta D tau, and delta D representing the normal, tangential, and total variational of contact distance. This formulation prepare our problem for numerical simulation using finite element method and semi-smooth technique. But before this, it's important to verify that the problem is energy consistency. The total mechanical energy is the sum of kinetic energy and hyperelastic energy. In the absence of external force, the balance of energy can be written as shown in the slide in equation 12, where W, C plus F plus A representing the dissipative work of friction and adhesion, while D representing the dissipative work of viscosity. Depending on the physical regime, energy is conserved in the absence of friction, adhesion, and viscosity. Conversely, as soon as this mechanism are active, energy is decreasing. Note that in the talon-corneal approach, the energy dissipated from adhesion is always positive, thanks to the fact that the adhesion force are active only when the contact gap norm D is increases. For detailed proof, we can refer to our paper. Now I want to present the numerical strategy based on the primal dual active set method. First, contact and friction are reformulated as a complementarity function. So persistent contact is representing by R lambda C, while Coulomb friction are representing by R lambda F. The physical condition can be representing as solving R lambda C and R lambda F equals 0 on the contact boundary. These functions are semi-smooth, but their expression depending on the physical regime. So we can identify three main regimes: no contact, gap, stick, and slip, with the corresponding formulation of R lambda C and R lambda F. For complementarity function for adhesion, we recall the KKT condition for our model talon-corneal. And for simplicity, we assume G0A equals 0. So adhesion force is expressed to the three main regimes: no adhesion, cohesion, and decohesion, depending on the value of gamma norm D. So the complementarity function for adhesion is given by R lambda A, where the KKT conditions are equivalent to solve R lambda A equals 0. Note that the complementarity function is applied to all three main regimes for adhesion: no adhesion, cohesion, and decohesion. The complementarity function are solving using semi-smooth Newton method. Let me now explain how apply this for adhesion, which is our focus. We introduce the generalized derivative of R lambda A, where K representing the indicator function for active cohesion zone. At iteration K, the semi-smooth Newton method update the adhesive parameter to ensure convergence to correct mechanical response. Note that the same approach is applied for contact and friction. To organize the system, we apply the primal dual active set algorithm. First, we define the set S of the node on the contact boundary. For each node P in S, its status is determined at iteration K plus 1 by active-inactive contact set, active-inactive contact friction set, and active-inactive adhesion set. The primal dual active set is based on the resolved nonlinear residual R combining the mechanical equation and the complementarity function for contact, friction, and adhesion. At iteration K, the iterative scheme works as follows. First, we initialize the variable U point lambda lambda A, and we set parameter and K equals 0. If the contact gap is positive, we set the adhesion friction and contact force to 0. Otherwise, we define the active-inactive contact friction adhesion set. And at iteration K plus 1, we solve for U lambda lambda A by applying the linear condition. Next, we update the parameter of adhesion GA and GA point according to their evolution law. And finally, we check the convergence. One key advantage of the PDAS algorithm is that it's allowed to solving this linear condition without introducing the parameter of multiplier Lagrange, which simplifies the computation. Now I want to present numerical simulation. We will focus on the dynamic and adhesion contact instant on the arterial wall. let's look the model stent artery more in detail. The material are representing by elastoplastic by compressible Cial-Leger monolaw with added viscosity. The first configuration is illustrated on the figure. Here, the tangential and the normal contact are penalized equally, and the parameter of adhesion and viscosity are chosen to ensure stable interaction from the first phase of contact. Now we want to examine the stent's final configuration after deployment under full adhesion with a high parameter of adhesion with PM equal 100, GM equal 10. In this scenario, we say the stent is fully attached to the stent arterial. So the simulation highlights the capability of our model to reproduce a stable interaction and a stable adhesion under full dynamic condition and academic. Next, we want to investigate how the adhesion parameter PM and GM affect the stent's final configuration. So we see different shaped form for different adhesion parameter PM and GM, representing a decreasing adhesion level. So we see a smooth transition from full adhesion to partial decohesion and total detachment. This result confirms that our model can be reproduced continuously the different regime of adhesion from full adhesion to complete decohesion. Finally, the table shows the total number of Newton iteration and CPU time for different adhesion parameter with added viscosity. The performance remained very satisfactory with the total number of Newton iteration with approximately an average of 2 to 4.5 per time step, which demonstrating the robust and fast convergence. This work represents a robust framework for contact with Coulomb and adhesion. It ensures energy consistency at continuously and discrete level, and it provides unified treatment of contact regime validated by simulation, while the numerical strategy is based on nonlinear finite element method with implicit time integration and PDAS algorithm. Future perspective include theoretical analysis for existence of solution, numerical extension to plasticity, damage, viscoelasticity, and numerical and application realistic to three-dimensional biomechanical simulation. And thank you for your attention.
So in the biomedical application,
Yes.
it is only adhesion or also the plasticity of the stent that make it stent shape?
Yes, and the stent on the arterial wall is the adhesion and the plasticity. But now we use just adhesion, but after we want to fix adhesion and the plasticity in the same time. We have another work on the plasticity.
So congratulations for the talk. I was wondering, when you are choosing the non-linear complementary functions, when you are defining the tribological strategy, can you please comment why did you choose those two functions? I think it was in the previous slide.
Here?
Those functions for the normal contact condition and the contact condition. Were you already familiar with those ones? Why did you choose those in particular? Those two complementary functions.
We have contact, friction, and adhesion. So for our model, we have the contact unilateral. It's represented by R lambda C, while friction is represented by R lambda F. We have not a complementarity function 1 for 2 model.
Yeah, for instance, for the normal contact condition, you could have chosen, for instance, Fisher-Wyss or some other forms. I was just wondering if probably for the adhesion form, people.
Yes, so it's just for simplicity, we use the sample form. Yes, of contact and MEM, and for viscosity, we use the sample model.
More questions? Please.
So just to get your example, what is the size finally of the full system?
I didn't understand.
What is the size of the full system you need to solve for integration?
For the simulation? The size of the stent? Or? We have the displacement field and the tensor stress and the adhesion force.
Got the answer? Okay, thank you. Okay, questions? If not, thank you very much again.